Hello everyone and welcome to my presentation. My name is Rohit and today I will explain why planets orbit around the Sun in elliptical orbits. This presentation will not be too mathematical, but rather an overview of the geometric and physical world behind orbits, showing the proof and deriving them. Also, this is a relatively difficult topic to understand, so you really have to pay attention. Now, my presentation is divided into four main categories. The first one covers the basic geometry of ellipses, and then I will introduce one of the most famous known laws, Kepler's second law of planetary motion. When these two concepts are correlated, there's an interesting fact about the velocity of planets, in which we can see in velocity space. Mind-boggling, right? Well, just see how simple it really is. Before we dive in, I would like to show a very straightforward illustration. Before this presentation, I arbitrarily chose 2 points at a distance away from each other. Now see what happens when you take this string and draw out with full outward force a curve around these 2 points. I have basically drawn to some approximation the orbit of a planet. I will leave this aside for now and will come back in 2 slides. For now, we can start by looking at the inverse square law, the fact that the gravitational force pulling at an object towards the Sun is inversely proportional to the square of the distance between the 2 celestial bodies. But how exactly does this give rise to an ellipse? Welcome to the first part of the presentation, Geometry Proofland. Remember that ellipse I drawn earlier? You might have noticed it is similar to if I used a single thumbtack to construct a circle, where the fixed length of the string guarantees that every point you trace out is a constant distance away from the circle. But with 2 thumbtacks instead of 1, what property am I guaranteeing about each point I trace out? Well, for any given point, the sum of the distances from that point to the 2 thumbtacks remain constant, right? I mean, I'm not changing the length of the string. So the defining property of the special curve is that the sum of the distances from any chosen point on the curve's circumference to 2 special points in the curve's interior remain constant. And these 2 points aren't actually called a thumbtack, they're actually called a focus, collectively called foci, from the Latin word foco, meaning fireplace, as one of the first places where ellipses were studied was for the Sun, a sort of fireplace in our solar system, sitting on one of the foci of the Earth's orbit. And before we dive into the orbital mechanics, it will be very important to look at the sum, from any given point to the 2 thumbtacks. Let's call the sum the focal sum of an ellipse. Now, the eccentric point and the circle center are 2 names for the foci. Now, I know what you're thinking. How does a circle center have anything to do with ellipses? Well, see what happens when you pick any circle, pick any eccentric point on that circle, and draw as many lines from that eccentric point to the circumference before rotating them 90 degrees about the halfway point. Wow, we have spotted our ellipse! Now, that was a lot of procedures, but these aren't just random. You will find a reasoning for each of these steps. Now, let's just carefully take each step one by one. I haven't just picked a specific circle, I just picked a random circle out of my head. The radius of this circle could be 1 millimeter, 2 centimeters, 5 kilometers. For all you know, it could be 100,000 light years. But to keep us in scale with planetary orbits, let's say that the average distance of the radius of this circle is approximately 1 astronomical unit, which is the average distance from the Earth to the Sun. Now, in that entire circle, I just picked 1 eccentric point out of all the infinite possibilities that there are. And after that, I drew as many lines from that point to the circumference, and finally, this step is very important, I rotated each line that I drew 90 degrees about their halfway point. And that is a very special and important step. Also, later on in the presentation, I won't have this diagram in the slides, so I've created a very stunning replica over here. My next point is a little more difficult to understand, so for simplicity, let's just take one of these lines. we have the line from the eccentric point to the circumference, let's call this point P, and then we have its perpendicular bisector, which we got after a special 90-degree rotation after rotating the yellow line, the eccentric line, 90 degrees about its halfway point. Now, fascinatingly, some of you might actually call this perpendicular bisector a tangent to the ellipse. So, what is the significance of this tangency line? The key insight here is that if you propose any point on this perpendicular bisector, you can find two congruent triangles and use them to conclude that the distance from P to Q is the same as the distance from Q to the chosen eccentric point. And using this logic, we can say that on the point of tangency, hence the point where the perpendicular bisector touches the ellipse, on that point, the radius is just equal to the focal sum, which if you remember is the sum of the two lines in the interior of the ellipse. And the reason for that is, again, because the hypotenuse are equal. So we actually find out that anywhere on the ellipse, on the point of tangency, the radius is equal to the focal sum. Now, this is very tricky. Trust me, I know from experience. But realistically, what is going on is that when you have two lines, one from the eccentric point of the circle and one from the circle center, both to a common spot on the circle circumference, the perpendicular bisector of the eccentric line is tangent to the ellipse. And more interestingly, on this point of tangency is also where the radial line from the circle center intersects this perpendicular bisector and where it is equal to the focal sum in length. Coincidence? Nope. And also, don't get me wrong, this setup and diagram does not have to look exactly like this. In fact, it can be anywhere else on that ellipse. Here, to make it easier, I've created an animation where the perpendicular bisector depends whether or not the radius is equal to the focal sum. And that point Q moving around the ellipse, the green dot, is any orbiting object around the sun, let's say the Earth. And that yellow dot is the sun sitting on one of the foci of the Earth's orbit. Also, the yellow line going from the sun to the point P on the circumference is all the infinite lines I drew at the starting diagram after picking an eccentric point. Now, you might be asking, well, why do the focal lines have to meet on the point of tangency? In other words, why does the radius have to equal the focal sum for this to work? Well, simply because on the point of tangency, hence the point where the perpendicular bisector intersects the radius, on this point, the radius is just equal to the focal sum, right? We discussed that in the previous slide. But because the radius stays constant, no matter which part of the circle you draw it from, the focal sum remains constant as well, which by definition means that it traces out an ellipse, specifically an ellipse whose focal sum is equal to the radius of the circle that it is in. Now, I've been saying that the perpendicular bisector is a tangent to the ellipse, so where's the proof? Well, firstly, at any other point on this perpendicular bisector, the sum of the lines going from Q to the eccentric point and Q to the circle center, their sum is always greater than the ellipse's focal sum on the point of tangency, which is just the radius. Here, I'm summing up what I mean by that. At any other point on this perpendicular bisector, the focal sum is always greater than the radius. What that means, and this is important, is that all the other lines on this perpendicular bisector have to lie outside the ellipse. And what this means is that the line we got after a special 90-degree rotation is tangent to the ellipse. So in the starting diagram, when I said what would happen if you picked an eccentric point and drew as many lines from that chosen point to the circumference and rotate them 90 degrees about the halfway point, is because we're basically just drawing a whole bunch of tangency lines to each of those lines. And these tangency lines will correspond to the velocity of an orbiting object in a particular point of an orbit. As the velocity is a vector, it also has a direction, and these lines will represent the direction that a planet is moving in any given point in an orbit. Until now, I have hopefully introduced some of the basic geometry of ellipses. But now awaits more theoretical ideas involved in astronomical calculations. Kepler's second law of planetary motion is just one of his three laws. It states that a planet orbiting the Sun sweeps equal areas in equal times. Thus, the speed of the planet increases as it approaches the Sun and decreases as it receives it. In this diagram, it takes 1 month for the Earth to traverse the shorter arc and 1 month as well to traverse the longer arc. When these two arcs are connected to the center of the Sun, it creates two triangular shapes of equal area. Thus, we can say that the area swept out by a planet for any given time frame is proportional to the time it took to traverse the arc. And that's all you have to know about Kepler's second law, that the time is proportional to the area for any given point of an orbit. In the next two parts of the presentation, everything before comes together to create patterns and formulae. Now, what do I mean by the shape of velocities? Well, some of you might know that velocity is a vector. Even though it has a magnitude or value like speed, it also has a direction. Feynman used this property to recognize a fascinating fact about ellipses. At every point on the Earth's orbit, there is a different tangential velocity for that given point, right? So at points near to the Sun, the line representing the velocity vector is longer when the Earth is further from the Sun. Now, because velocity has a direction, as well as a magnitude, it can literally be drawn. If you were to take every velocity vector on that orbit, measure them, and then connect them by their tips, you would construct a perfect circle. But again, we have to ask ourselves, why on earth should this be true? Until now, I was unable to follow Newton's complicated mathematics from his Principia, so I followed Feynman's more simple approach. In the next two slides, you will see the genius behind his work and his reasoning for that perfect circle on the screen. What I would like you to do is think about the time taken for this planet to traverse one of those equal angle slices, and how that time changes as you go from a bigger slice to a smaller slice, or vice versa. Well, by Kepler's second law, that change in time taken to traverse those arcs is proportional to the area swept out by the planet. But there's one more thing to notice here. Not only does the time taken and the area swept out change, but the arc length changes too in proportion to the radius. Take the blue slice. It has a shorter arc length and a shorter radius. And now take the red slice. It has a longer arc length and a longer radius. So a new formula we can write is that the change in time and the change in area is also proportional to the distance away from the Sun squared, or the radius squared. We can apply this knowledge to the inverse square law introduced at the start of the presentation. The resultant force of an object in a particular direction is just another way of saying its mass times its acceleration in the same given direction. But again, the mass of an orbiting planet or any celestial body does not change in an astronomical scale within seconds. So we can actually remove the quantity mass from the inverse square law in such a way that allows us to write acceleration in the terms of delta v over delta t. Change in velocity over change in time. That is what acceleration is. Simplifying, we can write it like this. Now, in the previous slide, we learned that the change in time is also proportional to the radius squared, or the distance away from the Sun squared. So we can actually substitute these two variables, and concluding, the change in velocity between two orbiting points actually turn out to be some constant. So, if you were to take any points in an orbit, measure their tangential velocity, and then subtract them from each other, your answer will always be a constant no matter which point and part of the orbit you pick from. And I did not just pick any 3 points in this example. I picked points that are equally away from each other in terms of the angle subtended by the center of the Sun. So, you will only get a constant answer if the points you picked were equally away from each other in terms of the angle subtended by the center of the Sun. So again, if you were to take as many velocity vectors in an orbit, measure them, and then connect them by their tips, you would get some sort of regular polygon whose side length is equal to the change in velocity vector. and this change in velocity vector, as mentioned in the previous slide, stays constant for any orbiting body. We can actually prove that this shape is a regular polygon by looking at the force vector pointing towards the sun. Because it is always, no matter what, always pointing directly towards the sun, it is turning by a constant angle. So, if we connect each force vector by their velocity vectors, we find that all the exterior angles of the shape are equal, making it a regular polygon. And yes, hypothetically, if you were to take all the velocity vectors in an orbit, measure them, and then connect them by one point, you would get some sort of regular polygon whose side length is again the change in velocity vector, but because you used all the infinite velocity vectors, this regular polygon does not have any corners or side, which is just a perfect circle. And fun fact, this perfect circle that we've constructed is what you call a velocity diagram. When you get all the velocity vectors in an orbit, connect them by their tips, you construct the velocity diagram for that orbit. And does this not look familiar to the starting diagram when I picked an eccentric point and drew as many lines from that point to the circumference? Yeah, I did that because we were basically just drawing a velocity diagram for that orbit. Oof, that was a lot. But don't worry, this is the last part of the presentation. Now that we've looked at velocity diagrams, we're left with deriving the ellipse using these very special velocity diagrams. As I mentioned, we've also seen that connecting infinite velocity vectors by one point will give you a perfect circle. But there's one more very important thing to notice here in our ellipse. In our orbit, moving theta radians off the horizontal axis with respect to the circle center gives you a velocity vector that is represented by moving the same theta radians off the vertical axis in our velocity diagram. So we come to the question, what special geometric curve, which is a shape, satisfies the property that moving theta radians off the horizontal in our orbit corresponds to moving theta radians off the vertical in our diagram? Is the question clear? And yes, it is an ellipse. But why on earth should it be true that moving theta radians off the horizontal corresponds to moving theta radians off the vertical? Well, take the velocity diagram on the left, rotate it 90 degrees clockwise about its center, and then rotate all the lines in it 90 degrees counterclockwise about their centers. This way the lines are still oriented right, we just place them in a different manner. We actually construct a perfect ellipse. So with the help of the regular polygon we've been trying to prove here, we actually construct a perfect ellipse. And you might be familiar with the diagram on the right when we tried to prove that the perpendicular bisector was a tangent to the ellipse. And yes, now you have to go back and ask yourselves, what was going on in that proof again? Well, one of the keynotes was that when you have two lines, one from the eccentric point of a circle and one from the circle center, both to a common spot on the circle circumference, the perpendicular bisector of the eccentric line is tangent to the ellipse. And what's more, is that on this point of tangency is also where the radial line from the circle center intersects this perpendicular bisector, again on the point of tangency. What this means is that the point on our little ellipse, which is theta radians off the horizontal with respect to the circle center, has a tangency slope perpendicular to this eccentric line. And because of the whole 90-degree rotation thing with our velocity diagram, this means that it is parallel to the velocity vector that we need it to be. So, this little emergent curve inside our velocity diagram has the exact tangency properties that we need it to have, and hence the shape of an orbit must be an ellipse. Thank you for listening.